Now the topic is adiabatic heating and adiabatic cooling and barotropic and baroclinic condition. First one is the latent heat. Energy absorbed or released by the substances during the changes of the physical state of the substances is known as latent heat. Normally, the substances changes the phases like solid to liquid, liquid to gaseous or vice versa. Then the substances absorb or released energy without changing the temperature of the substances. That is known as a latent heat. Okay. In 1762, British chemist Joseph Black first time introduced the concept of latent heat. Latent heat is very significant in climatic condition and weather phenomena, especially when we discuss the evaporation and condensation process. Okay. Here the temperature of the substances remain constant, but when the substances changes its phases from liquid to gaseous or solid to liquid or vice versa, then energy is released or absorbed. That is known as latent heat. Now come to the point of adiabatic heating. What is adiabatic heating? So there is no neat heat transfer between a system and its surrounding environment. That is known as adiabatic heating. Okay, in simply, there is no change of temperature, there is no changes of volume, and there is no changes of pressure of atmospheric condition. In spite of that, there is cooling. That is, cooling is basic reason behind the cooling is due to changes in height, due to changes in altitude. Okay, due to changes in altitude, there is a vertical movement of air. It may be ascending air that's moving upward, and there also descending air current that moves downward. Due to changing the position and due to changing the height, due to changing the altitude of the air or air masses, there is a cooling and heating. This is known as adiabatic cooling, adiabatic heating or cooling. So here the changes associated with the changing of altitude. The changes of temperature is due to the internal changes. There is no changes in temperature, no changes in volume, no changes in pressure. Only there is a changes associated with the changes of altitude or the height. Okay. We are all familiar with the adiabatic process. In lower class, we are all familiar about the orographic precipitation. In orographic precipitation, air moves upwards through the slope and expands and is responsible for the heavy rainfall. This is nothing but the process of adiabatic cooling. Okay, adiabatic heating and cooling is very common in the convective atmospheric condition. We are all familiar that the convective precipitation is very common in intertropical convergence zones, rather equatorial zones, rather doldrum zone. Throughout the year, there is this region received high insolation due to high pressure. This doldrum zone is a famous for the convective current. Okay, adiabatic heating and adiabatic cooling, there is no need transfer of mass or that there is no thermal exchange in between the system. Okay, the changes of temperature is solely due to the internal changes due to the changes of height. That is called the adiabatic. If the air moves upward, then there will be adiabatic cooling. If the air coming down or downward or the descending air current, then there will be adiabatic heating. Okay, go through this picture. Okay, we are all familiar with the normal lapse rate. there is a basic differences between the normal lapse rate and adiabatic cooling or heating, rather adiabatic lapse rate. In normal lapse rate, with the increasing height in troposphere, there is a decreasing trend of temperature. The rate of decreasing trend of temperature is 6.4 degrees centigrade per kilometer. Okay. If everything is constant, air is not moving, then only due to the increasing of height from the sea level to the uppermost part of the troposphere, it's called tropopause. Its height is not uniformly distributed above the equator or pole. On an average, height of the tropopause is 18 kilometers on an average. Okay, up to the upper limit of the troposphere, that is the tropopause, there is a normal lapse rate. With the increasing height, the temperature starts to fall. It at the rate of 6.4 degrees centigrade per kilometer. That is known as normal lapse rate. Okay. There is no ascending current, no descending current. There is no moving air masses, no air parcel. That is the standardized condition. But adiabatic heating or adiabatic cooling always associated with the changing of the height, changing of the altitude. Suppose there is an air mass, okay, and this air mass moves upward, and with the increasing height there is no neat heat transfer in between outside or the surrounding atmosphere or within the system. Due to changes in height, the temperature, there is a decreasing trend of temperature, and that is called adiabatic cooling. Okay, but normal lapse rate, there is no air parcel, just increasing height, there is no ascending air current. There is a normally a descending trend, there is normally a decreasing trend of temperature, that is the normal lapse rate in standardized condition. And in adiabatic cooling or adiabatic heating, there is an air parcel, there is an air mass, there is an upward movement of air mass, and it moves upward due to changing of height, it cools. That is called the adiabatic cooling. If it comes downward, there is an adiabatic heating due to changes of altitude or height. Okay. So changes associated with the changing of altitude, that is called the adiabatic heating or adiabatic cooling. Okay. It's very common in orographic condition or orographic precipitation. It's very common in the convective zone and the equatorial and doldrum region. Okay. And and it's the layer of atmosphere, troposphere, stratosphere, ionosphere, mesosphere, thermosphere, and exosphere. It encounters the decreasing atmospheric pressure with increasing elevation. Okay, decreasing atmospheric pressure with the increasing elevation. Air mass expand, the up or the moving air masses, the upward air masses expand until it reach the pressure of equilibrium. Okay, the expansion is result of cooling of the air mass. This is basically this fact is basically responsible for the adiabatic cooling. Okay. There is basically three mode of heat transfer. First one is the conduction. This is due to the touch. Okay, this is the basic principle of calorimetry. Then the convection. This is the vertical movement of the mass. And third one is the horizontal. That is the advection. Advection is the heat transfer or the energy transfer. Better to say energy transfer in between an object and environment due to the fluid motion, okay. Conduction is a process. It's conduction basically touch, heat transferred by the touch, by the direct contact. Atmosphere gets warmed through the process of conduction. This process take places when two bodies of uneven temperature are in contact. Okay, contact with one another. There is a flow of energy from the warmer to the cooler body. This is the basic principle of calorimetry. The heat transfer continues up to until both the bodies reach to the same temperature or the contact is interrupted. It continues up to or until both the bodies reach with the same temperature. This process is significant for the heating of the lowering layer of the atmosphere. Okay, basically it is due to touch or contact. Second one is the convection. Convection, we are all familiar with the convective current in equatorial region. There is a vertical movement of the air or air masses. The vertical air goes up and simultaneously is spread and expand, and it's cools, and then the air current moves downward. This is basically for the important for the convective surgeon. Air moves upward and expands and then moves downward. This is the convection mode. Convective heat transfer or energy transfer limited only to the troposphere. Okay. Then come to the advection. The advection is the heat transfer through the horizontal movement of an air. Horizontal movement of air is comparatively more significant than the vertical movement or the contact movement. Advection is the transfer of the heat or energy, better to say energy, between an object and its surroundings environment due to the fluid motion. Okay, advection is more important in the case of atmospheric circulation. Okay, we can take an example. It's very important for the fluid motion. Suppose in the coastal region of Japan, there are two types of ocean current, that is the Kuroshio or Japan air current. It's a warm ocean current, and Kurile current, that is the cold ocean current. Both current, warm and cold, warm Japan current and cold Kurile current meets in the coastal region of Japan. Subsequently, due to meeting of the two ocean currents, the adjacent atmosphere, there is a contrasting in temperature zone. There is a mixing of cold and warm atmospheric condition, or cold and warm air. And this is the horizontal merging of the two different or contrasting air masses or the air that is responsible for the advection. Advection is very important factor for the atmospheric circulation. Adiabatic heating or cooling related to the changes associated with the altitude, changes of the height. The changes of the temperature is due to or solely for the changes of the height. Second one is that there is no neat heat transfer in between the system or the outside of the system. The pressure and the volume of the air remain constant. It's common in the convective atmospheric condition. And adiabatic heating and adiabatic cooling is related to the ascending air current and the descending air current. Ascending means it moves upwards and descending means it moves downward. Ascending air current, there is a relation of the ascending air current and expansion of the air, and there is a relation between the compression and the descending air current. Compression and the descending air current. Compression of the air mass is accompanied by the increasing of temperature. Okay, that is the compression and downward movement of the air or the descending air is responsible for the adiabatic heating, and expansion of the air mass is accompanied by the lowering of temperature, that is the ascending air current expansion and adiabatic cooling going in are accompanied by the lowering of the temperature. The barotropic related to the two words baro and tropic. We are all familiar with the tropic. 23 degree 30 minutes north is known as Tropic of Cancer and south is known as Capricorn. So we are all familiar with the zone of tropic. This barotropic condition is common in tropical region, that's why it is called as a barotropic. Okay, its latitudinal ranges from 5 degree to 23 degree north south. Okay, what do you mean by baro? Baro is related to the barometer, that is the pressure, rather normal atmospheric pressure. That is the pressure condition in the tropical zone. This phenomena is very common in the upper layer of the atmosphere, but it's confined up to the troposphere, up to the tropopause. On an average, the height of the tropopause is 18 kilometers. It is not uniformly distributed over the pole and equator. Okay. Barotropic means it's related to the density of the air. Density of the air related to the pressure condition, and pressure is related to the atmospheric conditions, sorry, insolation or temperature. So first one is the pressure. Pressure depends on density, depends on pressure. Pressure depends on temperature. Temperature depends on the insolation or the thermal condition. All these phenomena are related to the barotropic condition. Okay, density depends upon the pressure. It's a surface of a constant pressure and constant density coincide. Therefore, geostrophic wind depend on the height. So, if the pressure, temperature or the insolation is constant throughout the region, so the pressure condition of the region is also constant or uniformly distributed. On the basis of uniform pressure condition, density of the air is uniformly distributed. What will be the result? The result will be, what will be the result? The isobar. Isobar means the line with equal air pressure, that is isobar. And isotherm means the lines, the points connecting connecting the equal value of the thermal condition, that is the isothermal. Rather, the temperature of those places are equal. So what will be the result? Isobar and isothermal line runs parallel. So this is the condition of barotropic condition. Now come to the next slide. The density of the air depends on the pressure, that is the isobaric value. Pressure depends upon the insolation or the received energy or the received EMR. As a result, isobaric surface, and that is the constant pressure surface, and there is also constant density surface. What will be the result? The result will be the isobar and isotherm lines runs parallel, and this is known as a barotropic condition. What are the significance of barotropic condition? Barotropic condition, there is no advection. There is no cold air advection or warm air and advection, no cold front, no warm front formation. So from the climatic point of view, the temperature and pressure is uniform throughout the area, and both isothermal lines and isobar lines runs parallel to each other. Wind are unidirectional and increasing with the height. There is no thermal advection. So from the point of climatic condition are significant in climate, so barotropic condition is not so important to control the atmospheric circulation. Now come to the baroclinic. Baroclinic condition. If the isobaric line and isothermal lines intersect to each other, that is known as a baroclinic. Baro for the pressure condition, clinic for the inclination. So both baroclinic isothermal line and isobaric line intersect to each other. This is the intersecting condition of isothermal line with the isober line. We are all familiar about the upper layer atmospheric circulation. In the case of upper layer of atmospheric circulation, jet stream plays an important role. In jet stream, zonal flow is very important. Okay, zonal flow is when the air moving from east to west, or rather parallel to the isobar. It is known as a zonal flow. So zonal flow is very important for the jet stream because its air flows parallels to the isobar. So the air moving from east to west, or east to west, or west to east, or the follow the isobar, it's solely due to the baroclinic condition. And the meridian flow, rest of the air motion out of jet stream. We are all familiar with the planetary air system that easterliest, westerliest, mid latitude westerliest, polar easterliest, trade wind are easterliest. All those are related to the direction of north south. Trade wind are northeast and moving from southeast. Okay, this southwest orientation and direction controlled by the baroclinic condition. Rather, baroclinic condition plays more important role, plays a vital role in atmospheric circulation than the barotropic condition. It's responsible for the creation of font and advection. Okay, geostrophic wind itself responsible for the itself a result for the baroclinic condition. This is a picture of a jet stream and Rossby index. We are all familiar with the jet stream and Rossby index. Here the barotropic and baroclinic condition are parallel, are intersect in each other in Rossby index. So atmospheric circulation and upper layer, basically for the upper layer of the circulation, baroclinic condition is most important. Jet stream solely governed by the baroclinic condition in the upper layer of the atmosphere. And now come to the last one, that is the Ekman spiral. Ekman spiral is not directly related to the adiabatic heating, cooling, or the barotropic or baroclinic condition, but it's very important for the atmospheric circulation as well as the ocean water circulation. So it's very relevant to include the Ekman spiral. Ekman spiral normally shows the theoretical displacement. It normally shows that this is the theoretical displacement. Theoretical displacement of current direction of the Coriolis effect or the frictional force. Okay, Swedish scientist in 1962 introduced the concept of Ekman spiral. Most probably Ekmans was the surname of that Swedish scientist. The deeper water deflection of the water mass duly affected by the Coriolis force, and that deflection always to the direction of the right angle of the moving mass, moving water, moving air, all these things. Okay, suppose this is the direction of wind moving. Here I would like to include one thing, that this incident explained by the ocean water but oceanic circulation, but it's equally applicable for the atmospheric condition. Okay, this is the wind is moving to this direction, and moving air, there is a frictional layer in between the water mass and the air mass. Okay, then wind try to push the ocean water to that direction, but due to Coriolis force and due to increasing the depth in the atmosphere, it's due to increasing the height, there is a deflection of the ocean water, and that is about the 45 degree. That then, and there is also the deflection in the lower layer. There is also a right angle deflection of the lower layer, and so on. At below the 100 meter or in the case of atmosphere or wind, above the height of 100 meter, the wind blows or the oceanic circulation moves just opposite to the upper layer. That direction and that will be the just opposite direction. Those angles are the equiangular deviation, equiangular deflection. That deflection looks like a spiral. That's why it's called the Ekman spiral. It is equally important for the atmospheric circulation. Coriolis force and the frictional force creates deflection, responsible for the deflection, and that deflection gradually decrease with the increasing of height in the atmosphere, and in the case of ocean water due to increase the depth of the ocean water. And that's why the equiangular spiral due to the Coriolis force developed, and below the 100 meter of water and above the 100 meter of in the case of atmosphere, the wind blows just opposite to the initial flow. That is called the Ekman spiral. Okay, thank you very much.